while our speaker is getting mic'd up, let me introduce him. So the second half of today's session seems to be a little bit themed, since both talks will have something to do with quantum computation. And the first of these will be soon enough. No worries. All right, so if you could just get mic'd up real quick. All right, so the first speaker is, or third speaker in the session, first on quantum computation, is Jacques Garrigue, who will tell us, well, how to understand it in a type-theoretic sense, so that we can finally make sense of it all. Or maybe just me.
Okay, so let's go. I'm going to talk in this order, basically. So introduce what is the unitary semantics, because we are going to talk about pure quantum computation, for which the standard approach is to give an unitary semantics. And then the next steps will be more specific to our work. First defining the notion of direct power vector space, and then through lengths and currying through lengths we can focus, and then we can prove circuit corrects using this approach. So what about the unitary semantics? So this is a very short introduction to the what is the unitary semantics of quantum programs. Basically, in the unitary semantics, the idea is that rather than having a qubit, normal bit will be a value of 0 or 1. A qubit is actually a vector of norm 1 in C square. So it's larger than a plane. And with the standard basis of will be then the vectors ket 0, you did with this ket 0 is 1 0 and ket 1 is 0 1. Now what happens when we have n qubits? We are not just going to take the normal Cartesian product, we are actually going to take a tensor product. This creates a huge state space. So we take the n iterated tensor product, which is something like that, which is actually going to be c to the power 2 power of n, something huge. And then the computational basic states are the tensor products of the individual basic states. And we can, of course, obtain the other states as linear combinations, with, of course, we must still be of norm 1. And the idea is that, in particular, those that can be expressed as an n-ary tensor, that is just a product of specific states, not necessarily basis state for the individual ones, those are entangled, and they express the particular power of quantum computation. The fact that you can two qubits can be entangled and have a non-trivial state. And then how computation works is that pure operations are going to be unitary transformations that are linear or non-preserving transformations on those states, on that space which is called an Hilbert space. And so how do we get complex computations? Basically, we start from basic operations, which are in transformation called gates. So I just show here two basic gates. One is the Hadamard gates, which, if you look at the matrix, maybe you will see that it's a kind of rotation. This is a rotation in a complex, C2, so it's a bit strange kind of things, but it's a rotation. And you have the C0 gate with a conditional note. So it's a connection between two qubits. So dependent of the state of the first qubit, we are going to swap the 0 of 1 of the second qubits. So if the first qubit is 0, this is the identity. When you see this at the matrix, if the first qubit is 1, we are going to swap the two. So this one is swapping the two qubits and the value of 0 and 1. Okay. And sorry. And with this, we can build actually big circuits. One example is Shor's 9-qubit code, which is something that is able to, the idea is you have an encoder part and a decoder part. And if you are going to encode 1 qubit, all the others are set to 0. And then there will be E, which is a possibly noisy quantum channel, which is also encoded as a unitary we can see it as a unitary transformation. And the point is that, and then we have a decoder, and if there is only, this is able to correct just one error. If there is only one error in one of the 9 qubits, this will be able to revert the first one to the correct value. So a quantum circuit is going to apply unitary transformation to input state to an output state. This transformation can span several qubits. So here I have of the first and the fourth, and here the first and the seventh. Or this can be individual one, like the Hadamard gates. And they are applied sequentially. So, what's the semantics of this composition? Because what we've seen, the semantics for individual gates were just on a smaller space. And here we're moving to a larger space. So we need a way to apply a gate to a larger space. So for pure computation, the whole circuit can also be described for a matrix. That's a traditional view. And application of a gate then will use a form of padding where you're extending the side of the matrix to adapt it to the whole state. So what we're going to use is taking the tensor product with an identity matrix and then reordering. So here, if we look at the first CNOT gate, it's using qubit 1 and 4. So what we are going to do, first we have set 7 extra qubits. So here, all the ones we replace by actually an identity matrix of size 128 by 128, huge one. And then we need to remember to reorder the second and fourth qubit because we want this one to be there. Okay. So this represents actually another matrix of the same size, 512 by 512, which is doing a tensor permutation, extending second and fourth component of the tensor product. So that would be the transitional way to express that in the semantics. Well, problem with the semantics is that the size of matrices becomes huge. Here we are talking about all the matrices are 512 by 512. And in particular, all the reordering are going to be cumbersome. And when we're taking the whole product of all the steps, actually what we get is a completely non-trivial matrix of this side. Okay. Well, of course, people are doing proofs using these semantics. And how do they do that? Well, they will use things like a symbolic representation of the Kronecker products to avoid this blow-up of the size of the matrix. And also another approach is to use a labeled direct notations to apply the different gates individually, actually to get things that would commute nicely. But all this actually, in our view, comes at some cost in terms of compositionality. What I mean by compositionality here is that if you look at this code, actually, it's composed of two simpler codes, which is the bit flip code and the sign flip code, and which are themselves able to fix simpler errors in the channel. And you can see that actually this is really a combination of those two on taking more individually actually to parts of this code, the encoder and decoder parts. We're using the encoder, decoder part of this code, we can build the big one. And we would like to see all these parts as individual gates that we combine. So we want to do everything compositionally. And we want to avoid to be bothered by all the permutations in the middle. So how can we have a nice representation of that allows to represent this circuit in a compact way and then do proofs on that? This is the goal at the end of the day, doing the proofs. Okay. So, well, the first step is that we're going to use a different view on what is our circuit. And we use the isomorphism that C square can be seen as actually a functions of 0 and 1 to C. Okay, simpler. Then the basic states are going to be, well, the state 0 is take x. If x equals 0, then 1 else 0. And if 1 is if x equals 1, then 1 else 0. And linear combination of those can provide all the states. Same thing. And the nice thing then is this extends very nicely to n qubits. Then if I have n qubits, this is just 0, 1 to the power of n, which is going to be of the same size. And this one, then we consider the individual state to be just, we take a vector of normal bits. And if the input state x is the expected one, then it's 0. Otherwise, it's 1, else it's 0. So actually, expressed this way, it looks a bit like probabilistic programming, if it were not C but R, which is not too surprising because another actually semantics for quantum programs use this, where you will use actually the norm of the individual, the square of the norms to get a probabilistic semantics. If you include measurement, you need that semantics. Okay, but then the next step, in order to do what we did to tensor products, the next step will be a generalization when we define the direct power vector space based on this. And what's the idea? Is that rather than going to C, we are going to go to any vector space on a field K. Okay, that's just a big generalization. We generalize also finite type. This was just 0, 1. We could have anything, but this part doesn't matter. You can just fix that the finite type is just 0, 1. And then a basis will be the same thing as present on the previous slides. It's just that here we go back to actually this being just C. If I take K to the 1, actually, this is, you can see it just as the complex. And the interesting part is how are we going to represent our transformations on this? They're linear transformations on that space, okay? T to the power 2 to the power of m. But we want this to apply to any vector space. This will allow to do the nesting. That we had the problem that we needed to do nesting to accommodate for the extra qubits that were not involved in the transformation. We will just hide it in this T. And so we want this to be a function that works on any vector space. Okay. Problem. How do we answer that functions in this type have a Unix matrix representation that does not depend on T? Because in Coq, actually, you cannot say that in Coq, even though actually this is a parametric representation. Okay. And the answer is that the solution is just to additionally require naturality for this transformation. So naturality is the standard actually category theoretical definition of naturality is that if you bring any linear map, you're going to say that composing G applied to T1 and then the map, or applying first the map and then G applied to T2 is going to be the same computation. This is just standard naturality. I don't go into the details for that. And then this will give us our notion of morphism of unitary transformations are going to be, they are linear, natural, and unitary. If you remember this morning talks by Jeremy Gibbons, This is the same property he had for the deconvolution, except maybe these are not exactly the same definition of linearity and unitarity, even if it's the same naturality. But it's funny that we have the same notions. So here, morphisms just are those linear morphisms that satisfy identity naturality. A special case is the endomorphism. If I have a matrix, of course, I can produce such a linear transformation that is natural. We can compose those morphisms and still keep the naturality, no problem. And we can define a notion of naturality. We just did the notion of inner product. So a morphism is unitary if it preserves the inner product. That is the idea. So we keep it as an external property because it needs to be proved independently. And if you add the measurement, actually you end up with things that are not unitary in some cases. So it's important to keep it independent. Okay, that was the second step. Let's go to the third step, which is how we really apply those gates, those transformations to the whole circuit. And for this, we will use a notion of length. So the idea is that the length itself is a choice-wise of wires that are going to be connected by the gates. It's a basic combinatorial data. Garrigue is going to quotient the unused wires away. Here I have a gate that takes, well, 3 inputs in some order, and return them in the same order, okay, and ignores the 2 others. And focusing is going to composing, curry, get, and uncurry to build actually a transformation on the whole system. Okay? So what is a length? A length is just actually an injective function from M to N. So it's just a choice of the wires that we want to use and in which order. That's just what an injective function will give you. And with this, I can define extraction. So if I have a tuple, I can extract a tuple of length n. I can extract m components from it. I can also merge the tuple of length m with a tuple of length n minus m to get a tuples of length n. That allows you to transformation and put things back. I can use the complement of length. In that case, we lose the order because it does not matter if you're talking about the extra wires, we'll just keep them as identity, so we don't care about the order. And we can also, of course, compose lengths. And we come to actually the most important slide in the talk, which is the currying step, which is how along a length, using a length, we can change the structure of our quantum state. Basically, the idea is that if I have a quantum state of size of n qubits, I can just decompose it as seeing it direct power m to direct power n minus m to t. Okay, that's the basic idea. This is a natural isomorphism that we have. And then currying is going to be, first I take my n qubits and I want to decompose just to get m qubits and hide the others under. So it means that I'm taking the state of those m qubits, well, the indices. Here I'm just getting the indices. And then I will get the extra indices. And then I'm going to merge the indices from the both sides along the length to get how I should access my state. And this will just get the relevant part of the state that I need. And this will get something of the right type if I do it. And inquiry is the opposite operation where I just get one vector of indices and merge the 2 vector indices. These 2 operations form a bijection. And this allows us to change our view of the quantum state. So that we can define focusing. And as I said, focusing is first curry, so that we hide the irrelevant wires below, applied, our transformation with the hidden part is of side n minus m here. That part, the part we don't care about, and then uncurry. So this version is going to be linear. We additionally need to prove that it's natural to get a morphism. Okay. What properties do we get on this? Well, we can define composition focus. That is that if I have a composition of morphism applying focus to it, well, this commutes basically. We can also apply focus to a composition of lenses, and we have an important property is that if two lenses are disjoint, we can actually change the order of the operations. And last, for unitarity, if f is a unitary transformation, then focus of f is also a unitary transformation. These are the basic operations we need. Now, last part. I don't know how much time do I have left. A few more minutes. Okay, so last part is how do I use it to prove circuits correct. So first, the big slide at the beginning, the shortcode, I can write it actually this way. This is each individual part is going to be encoded as focus of the morphism version of a matrix. So I have matrices describing the gate for C0, Hadamard. Toffoli is the one, is a C0 with 2 control bits. And I just indicate to which, with a lens, to which parts I want to apply it, to which qubits I'm applying it. So the first one is I have a C0 applied to wire 0 and 1 and then to wire 0 and 2. And the decoder is doing the same thing as the encoder, but additionally after that there was a Toffoli gate. If you look back at this is this circuit, this is exactly the same thing. So these are those two, but additionally we have this Toffoli gate, which is in the opposite order. Okay, that's what I'm defining here. And then I have this Hadamard. Based on Hadamard, I have 3 Hadamard gates in parallel on wire 0, 1, and on 2. So that I can define the string flip encoder and decoder are just the B flip encoder and decoder, but composed with these 3 Hadamard gates. And finally, my encoder is just composing the 3 bit flip encoders on the right, on 0, 1, 2, 3, 4, 5, 6, 7, 8, with 1 6 flip encoder. And decoder will be the symmetrical operation, so I don't write it here. Okay? And then how am I going to build the proof? So the proof is going to be piecewise. That's the point of being compositional. So I prove properties for individual gates. For instance, that C0 applied to 0 and I, 0 and I, and 1 and I is going 1 on flip of I. Well, same thing for Toffoli. If it's 0 and 0, it's going to be the same thing. That Hadamard is involutive. That's a well-known property. And for the bit flip, and I can prove that actually, one interesting one is that bit flip encoder, if it's 1 JK, it will be 1 flip J, flip K, the result. Okay? Then actually the bit flip and SIG flip, I can prove that they are going to be equivalent to Toffoli if I am a perfect channel. That is, I just composing the encoder and the decoder without error. I just get a Toffoli gate actually. And finally, I prove that applying the shortcode to I on 8 zeros will be the identity. So the proof is 18 lines in total, and give you just a width of the proof is that using this operation, which has focus DP basis and deep merge DP basis, the idea of the operations is that we are applying focus to a basis vector, and this is equivalent to actually extracting the relevant bit from the basis vector, applying f, and then we do some computation, and later on we have deep merge DP basis. If we are able to return the result of operation to basis vector, then we can just merge back the bits of the basis vector. And if you're not able to go back to the vector, it's still okay, because we can, of course, decompose any state in the basis vectors. And I'm the end, it's the last important slide, but I'm not going to explain the details. But this is half of the proof for the bit flip encoder, which shows that by here the gray ones are applying the tactics. We can go step by step, starting from the 1jk to here 1 flip j flip k. I say that the ultimate result was 1 flip j flip k, so there will be again the same steps. So the only the tactics are the gray ones. The other ones show you the intermediate states. So that's basically how we do the proofs in this framework. So I move to the conclusion. So we have provided an alternative curve of pure quantum computation that's based on quantum states seen as a function, currying of this function for focusing, parametric polymorphic definition of transformation, and characterizing parametricity by naturality. And this approach allows us to prove a number of pure circuits. So here I've shows 9-qubit code. Also, there is the DHZ state preparation on the reverse circuit. And our conclusion is the ability to manipulate state through currying really seems to simplify at least some proofs. And then, thank you.
All right, thank you very much, Jacques. And let's maybe have one quick question while Jennifer sets up. All right.
So I didn't understand this. So I thought I understood the story with naturality, but now that you have given a conclusion, I've understood it. So, do you what is happening with naturality and parametricity? So usually I want naturality. I'm in Cox, so what I do is I ask for the plugin that tells me the parametricity lemma that generates it, and then I get this sort of naturality. But I'm feeling that you do the other direction.
Well, the problem actually, if you we didn't use the plugin for that, and the problem is here that it's actually, if you look here, it's restricted. This one is restricted to the vector spaces. So I don't think that the plugin will give me the naturality in that case.
All right.
So actually, what we do is by hand prove the naturality, and then use it.
All right. Okay. Thanks.
Okay. So let's thank Jacques again and have Dennis also back.